No.
Okay. We're on chapter 9, electromagnetic waves. And we're talking about this is called a transverse wave. So there's the crest, there's the trough. What do we call it from one crest to the next? What is that called?
A wavelength.
All at the same time?
Wavelength.
Very nice. The wavelength of the light. Or of water waves, if that's what we're talking about. But in this class, we're going to be mostly talking about light when we talk about waves. The amplitude is how tall the wave is. That's A, amplitude. So the distance from the center to the top. And the frequency is another thing you need to know. That's the number of waves that cross a certain point each second. We call that the frequency. So if you're standing there watching water waves, let's say that one wave goes by every second. Those are pretty fast water waves, but it could happen. That would be a frequency of 1. 1 hertz. Frequency is measured in hertz. So 1 hertz is 1 wave per second. Now light waves usually come by a lot quicker than 1 per second. What's your favorite radio station? Does anyone listen to anything but satellite anymore?
92.7.
92.7. So when you're listening to 92.7 on your radio, you're actually listening to the 92.7 megahertz is the wavelength of the sound you're listening to. So you're tuning in to waves that are coming in at 92.7 million waves per second. 92 million waves every second. Those waves. Encoded in those waves that your radio is receiving is music and sound and stuff like that.
Oh.
And those waves are being shot everywhere?
Yes.
Like there's radio waves coming through like right now.
Right now. You're just not tuned into them. Your head can't pick them up. It goes right through. But the radio receiver can pick them up. That make sense? Isn't that cool?
Sweet.
Sweet.
And they go through walls and everything?
Radio waves can go through walls. Yeah.
So, have you ever heard that thing where it's like the really high-pitched sounds, like some people can hear, like some people can't?
Dog whisper.
Like, does that have to do with how fast the waves are going?
Yeah, so your ear can pick up waves between 20, pick up sound waves between 20 and 20,000 vibrations per second. If it's vibrating faster than 20,000 vibrations per second, you can't hear it. But your dog can hear it because they can hear higher pitch. Do you want me to create a noise?
Yeah,
That's a different wavelength and see if you can hear it? You don't like this?
I can hear it.
This activity? I mean, it's not on yet.
He thought it was funny.
Let's see, I gotta find the app. It's a cool app. Here we go.
Dog whisper.
No, that's not.
I hate this noise.
Wait a second.
Well, this is awkward.
Okay. Hold on.
Charlie better entertain on that.
I don't know what to do.
Selfie it to
Oh, there it is.
Coming at you live from Mr. Willis.
Here we go. You ready?
you. Ready?
What's up, what's
so
up?
I'll make a sound here. That's 640 waves per second.
Let's go higher.
I can't.
So we'll go higher. We'll go up to 800.
Sheesh.
800 waves a second.
Go to 1,000.
1,000 waves a second.
Go to 1,500.
4,000 waves a second. 5,000 waves a second.
Can certain people not hear that?
Like
7,000 waves a second. 8,000.
There's been banging here, sir. Yeah.
Yeah, the older you get, the worse your hearing gets. That's 10,000 per second. 11. I just lost it.
Oh.
You lost.
You lost it?
Yeah. 12,000.
We
I
can
can't
hear
hear
it. I can hear it.
I can't hear that.
Oh, is it scary?
I can hear that
Anybody
clearly.
hear it?
How'd that make
Yeah, I
you?
can hear it.
Raise your hand if you can keep hearing it.
Okay, I'll keep turning it and tell me when you lose it.
I can still hear it. I can still hear it.
16. It's at 16,000.
I'm out.
I
You know,
can hear
it's
it.
like a.
17.
Wait, everybody be quiet.
I can feel it. I can feel it more than here.
18.
Nah,
Okay, it's going.
Nah, I can't hear it.
So you're around 18.
Yeah.
We're at 19 now. Can anyone hear 19? Babies can. So you lose it.
I feel like I can, like, you know what I'm talking about?
A baby will react to it. And the dog can hear that fine. That's 20,000 right there.
Oh, it's shot.
There we go, it's back.
Yeah. Still have it.
What's left?
All right.
What can dogs go up to?
Wow.
30. 30,000.
Everything.
They're having
Bats. 80,000.
Oh my god. I was about to say, yeah, because they have the.
Dolphins like 80 or 90.
Can I use a calculator?
No.
Oh no, you can't.
I'm trying to cheat, Hunter.
All right. So, another thing you need to know is C, the speed of light. C stands for the speed of light.
Which is 300,000.
300,000 kilometers per second. Or 180,000 miles per second. Think how long a mile is. Light can go 180,000 miles in 1 second. Light is very fast. Think how far a light year must be.
Crazy.
How fast light can go in a year. It's a long way. If light can go 180,000 miles in a second, think how long it can go in a year. That's a light year. The nearest star is 4.3 light years away. That's the closest star other than our sun. Isn't that cool? You know how far the sun is in light minutes away? Anyone know?
5.7.
8 minutes. The sun is 8 light minutes away. What? Come here. What do you want, test?
Yes. Gotta be kidding me.
You're messing up our video.
Thanks for disrupting class.
Oh, wait, I'm in the video now.
Are you pushing up forward?
Taking the line. Here it is. You're welcome. All right.
We'll be back momentarily.
Now,
They have a Miss B's class.
you want to go in her room
Sure.
or the academic center?
Okay.
That's what they made that place
Yes,
for.
sir.
See ya.
Now, when trying to understand what light is, we need to understand a couple things. First, a magnetic field. Have you ever heard of a magnetic field before? If you take a bar magnet, or if you take the Earth has a magnetic field because it's like the Earth has a giant magnet inside of it. And that's because the center of the Earth is mostly metal. And there's a bar magnet has a north pole on one end, that would be where our north pole is, and a south pole on the other end. And the field lines go from north to south. So if there's a magnetic field created that will turn a compass needle, for instance. It turns a compass needle along the magnetic field. So that is what a magnet produces, a magnetic field around it, which can have an effect on any particles nearby. We have a magnetic field around our Earth that takes particles from space, will hit the magnetic field and be funneled away from the surface of our planet, will be deflected by our magnetic field. Our magnetic field protects us from cosmic rays and particles. So, thank your magnetic field next time you get the chance.
Thanks.
So every charged particle has a magnetic field associated with it. And an electric field. So this is a positively charged particle, and anything that has a positive charge will have an influence on anything around it that is also charged. And you see that influence is drawn by these field lines here. So let's say this is a positively charged particle, like a proton, for instance. Do y'all know that protons are positively charged?
Yes.
So that has an influence on any other charged particle near it. For instance, if it's another proton, this positive charge will repel that other proton. And the closer the proton is to it, the greater the effect. So if you put the two charged particles near one another and they have like charges, they'll repel one another and they'll go away. And the closer you get them together, the greater the repulsion. Y'all see what I'm saying?
Does the moon have an electric field?
It does not, because it doesn't have much of a metal core, and it's also not spinning very fast, so it doesn't really have much of a magnetic field. This is a negatively charged particle that has the opposite effect as the positively charged particle. You can see the arrows going outward there, and the arrows going inward here. But the way we describe the way what light is, it's a vibrating field. It's a magnetic field and electric field interchanging with one another. So let's pretend we have a vibrating particle. Imagine that we have a string, like a rope. I guess we could actually get one in here.
Let's do it.
Let me get a string.
That's enough of that.
Drop the string.
Oh, I have to go up these ones.
Okay, I have string. We've got string.
Sweet.
It's a part of that.
Aubrey, hold this end.
Guess we have string.
Okay. So, let me cut the string here.
Get a little longer.
Give some slack.
Get a little longer.
Easy enough to make this model. So, imagine I have a vibrating charge. Now, hold it still. Okay. Hold it still. Now, if I vibrate up and down, we get a wave that runs through the string. You see how the wave it would be better if it was. You see how the wave runs through the string from me to Aubrey when I go up and down? You see what I'm saying? And if I do it over and over again, I get wave after wave after wave going through there. It's this string that doesn't work as well as if you had like a rubber band or something like that. But
Slinkies or something.
Slinky is perfect, yeah. But the point is, if I have a vibrating charge that's moving up and down, it will create a wave that goes out from the charge because of its up and down motion. So we have, again, here's our vibrating particle going up and down, creating this curved wave because it's vibrating up and down. Again, if it wasn't moving, it would just have straight field lines. But since it is moving, the lines go up and down. You see what I'm saying? That's what produces light, a vibrating particle. Now, what you need to understand is light is just a single frequency on a vast array of possible frequencies. Something that's hot vibrates really fast and produces these waves that come in at a certain frequency. And for instance, so we're looking at these lights up here. The reason why you can see light coming out of those lights is because it's hot in those lights. There's gas in there that's been heated up so fast, and the particles are vibrating, and they're vibrating so fast, these vibrations go through the air and through space and hit your eye. And your eye can pick up vibrations that are of a certain frequency. As a matter of fact, or of a certain wavelength. And it says there's a table. Let's see if it's in this chapter. It might be in the next chapter. I think it's the next chapter. Yeah. There's a table that shows the frequency of visible light, but the frequency of visible light is only a tiny bit of all the possible frequencies. If something is cooler than light, it can give off waves, but you can't see the waves. Just like if a sound is too high or too low pitched, you can't hear it, but it's still there. So, for instance, this desk right here, it's not glowing, right? This desk isn't glowing. The only reason I'm seeing this desk is because the light is bouncing off of it and hitting my eye. But if the lights weren't on and there was no light in the room, I wouldn't be able to see the desk, right? But the desk is giving off radiation because this desk is made of molecules and the molecules are vibrating. So there is waves coming out of this desk from its slowly vibrating molecules. It's not visible waves, but there are other types of energies. There's radio waves. Have you heard of those? There's infrared waves. That's heat. There's microwaves. There's X-rays and gamma rays. There's all sorts of radiation, ultraviolet rays, that you can't see, that your eyes don't pick up, but they're there. And so, believe it or not, this desk right here is releasing heat waves, and it's releasing radio waves.
Whoa.
This desk is. Every object releases waves because all objects are made of vibrating atoms, and as those atoms vibrate, they give off waves that come out of them. The waves consist of an electric field that vibrates this way and a magnetic field that vibrates perpendicular to it. Now, why these fields are there is a kind of beyond this class. It's more of a physics class. But I'll show you a little video of it that might give you a better sense.
Hi, it's Mr. Anderson, and this is AP Physics Essentials, video 124. It's on electromagnetic waves, which are the oscillations that create electromagnetic radiation. And they're important. And so light is electromagnetic radiation, and therefore it's carried in these electromagnetic waves. And does light make it from the sun to the earth? Of course. And so that means that electromagnetic waves can make it through the vacuum of space. But can you hear the sun? No. And that means that the mechanical sound waves aren't able to transfer through space. If they could, scientists have estimated that the sound of the sun would be around 100 decibels. So that's about the sound of a jackhammer a few meters away. So it'd be deafening in sound. So it's a good thing that we don't hear the sun, but it's really important that we see it, that those electromagnetic waves make it here. It keeps us warm. It also allows plants to grow, and so we can survive. And so the electromagnetic spectrum is made up of these electromagnetic waves. And they go from high energy, really high frequency, low wavelength gamma rays, all the way down to long wavelength, low energy radio waves. Remember, you're only seeing a small portion of that. But the one thing these all have in common is that they're made up of electromagnetic waves. Those are transverse waves. Remember, what a transverse wave is one where the oscillations are perpendicular or at 90 degrees to the direction of the movement of the wave. And so it's not only in one dimension, we also have electric fields and magnetic fields that are perpendicular to themselves. And so we have oscillations that are both perpendicular to the direction of motion and the corresponding field. And so they can travel through anything. Electromagnetic waves can travel through medium, like light can move through water, obviously, or radio waves can move through the walls of my house so I can hear the radio, but they can also move through the vacuum of space. And so if we look at electromagnetic waves, remember as we move towards high energy gamma rays, our wavelength is decreasing, but our frequency is increasing. So radio waves have these really long wavelengths around the size of a building, whereas gamma rays would be more the size of an atom itself. But if we look at how they oscillate, remember the wave size of an atom itself.
Let me stop. Trying to get okay. So do you, this is a good diagram up here. So do you see how radio waves are longer wavelengths? Imagine a particle that's vibrating slowly will produce a longer wavelength. So if I move my arm slowly, I produce a big long wave. Whereas if I move my arm quickly, I produce a lot of little short waves. You see what I'm saying? So slowly vibrating particles produce long waves. That's cooler stuff. Cold stuff produces long waves. And hot stuff vibrates really fast. The particles are vibrating really fast in something hot. That produces really short waves. So I just got my shoulder x-rayed yesterday. And they shot, look how high x-rays are. They're real short waves. And they shot those through my shoulder to get a picture of it. And those rays can be damaging. You don't want to get too much of that high energy radiation. The stuff on the right can be damaging to living things. The stuff on the left, not so much. Okay, sorry, I had to interrupt there. I thought it was continuing.
Long wavelengths around the size of a building, whereas gamma rays would be more the size of an atom itself. But if we look at how they oscillate, remember the wave is going to move in this direction and the oscillation is going to be perpendicular to that. But adding on top of that, we also have these fields. And so the direction of the wave is going to be, we'll say, from left to right in this dimension. But we're also going to have, in the z dimension, we're going to have these electric fields that oscillate back and forth. And then in the y, or rather in the x, we're going to have magnetic fields that go back and forth. And so to give you a visual of what they really look like, we have these oscillations in these two dimensions, and then the movement is going to be in the third dimension. And that starts to explain why we have things like the right-hand rule when it comes to electricity. And so energy can move from point A to point B in two ways. It can move as a particle. We could shoot a particle from A to B. But the other way we can transfer energy is through a wave. We could oscillate, for example, the water here, we could oscillate back and forth. That would create waves that could move B back and forth. Now that would be a mechanical wave, because we physically have to have a medium to transfer the energy from one to another. But electromagnetic waves are not mechanical. That means they could move through the water, they could move through the medium, but they could also move through the vacuum of space. And so did you learn to describe the model of an electromagnetic wave? It's both a transverse, perpendicular to...
Okay, so let me stop that again. So when a particle vibrates, when a charged particle vibrates, like an electron, for instance, an electron goes around the nucleus of an atom, right? Well, that's like a vibrating particle. So when a particle is vibrating, it produces this wave, and the electric field goes up and down like this, but every electric field produces a corresponding magnetic field. And if the electric field wave is going like this, the magnetic field wave goes like this. So you have two waves going across one another, and that's what this diagram is trying to show you. The up and down wave is the electric field. The back and forth wave this way is a magnetic field. They call light electromagnetic radiation. Have you ever heard it called that? It's because everywhere where there's an electric field, there's also a corresponding magnetic field. And it's hard to understand why that is, and we don't really have to understand why that is for this class. But it just is. There's an electric field and a magnetic field that correspond to one another, and they kind of go through space like this. They don't need a medium to travel through. They can go through the empty vacuum of space, and they will move on forever at the speed of light. This is how I dance, by the way, at Ziggy's. And I'm just moving along. They call me the electromagnetic kid, and it's very popular there. So, did you get any of that stuff?
Oh, it's all in there. It's good.
That was good stuff. I want you to notice something about these waves. Do you see how the waves are real intense near the disturbance?
Yeah.
But they kind of smooth out as you get further away? That's how all waves work. So, as they spread out, they get more diffuse, and they aren't as intense. So when you're very far from a star, it doesn't seem so bright. But if you were right close up next to it, it'd be crazy bright. So the intensity gets spread out over an area. And that's a good image of how that works. I don't know what kind of, that doesn't look like water. That might be mercury or something like that they made those waves in. But that shows it really well. Now, light can behave as any other wave does. Light can reflect off a surface. That's what's happened. That's why I'm seeing this desk. Light is hitting it from the window, reflecting off of it, and hitting my eye. Also, if it's something that's transparent, light can be refracted by it, like a lens. Light can actually hit it and then go through it. And usually, when light hits something, it'll change directions a little bit as it's refracted. Did y'all ever study that in physics or physical science? Incident rays and refraction and that sort of thing? Y'all had that?
Miss McVeigh, yeah.
Yeah, it's good stuff. And another thing waves do is waves can spread around corners. So if light waves are coming up to a barrier, they will spread out. They'll get refracted by the edge of the barrier and spread out to the sides. This is why, do you remember the moon? When it went in the shadow of the earth, you could still see it was red because some of the light got refracted around the earth and it's hitting the moon. Do y'all remember that? That was great stuff. If light goes through a little space right there, it'll go out in all directions from the little space. Because of this type of refraction that you see, shadows, thank you, shadows are not, if you ever look at a shadow on the ground, it's not a straight line, it's kind of a blurry line. Do you notice, Aubrey, that shadow is not nice and straight, it's a little bit blurry? And the blurriness of the shadow is due to this refraction. I wish I had a better shadow to show you. That's pretty good right there. It's a little blurry because the light's spreading out as it comes around the edge. You want to get it on camera?
Oh yeah.
Do y'all want to see? Do y'all want to stand up and see the blurriness? Jack, can you see?
Check that blurriness. Check that blurriness.
See how that's blurry right there. It's not a nice straight line. It gets blurry the further you get away because that light's refracted. So these are all properties of light. Now, let's go back and look at, let's start the next section, which you'll need to read. But I want to get started on it. Here it is. So 10 points if you can get what this is from. That was loud.
Do that
Try it
again.
again.
So let's not do it so loud.
I'm trying not to do it so loud.
Now I'm only gonna be able to hear like 640.
Hold on.
One more time.
All right. Purple's correct.
You know it. That's right, Chris.
Blue is incorrect.
Wait,
Green is correct.
Got it, bro.
Good job, Chris.
Peach is correct. That's for Family Guy. That's stupid for Family
What?
Guy.
Look, turn around.
Why didn't you turn it in?
Because I was about to get up and you kind of said it.
Ooh.
So
Too
you
late.
know what that is? That's a big old radio telescope dish. That can pick up radio signals. Radio signals are long wavelengths. Remember somebody asked, can it go through walls? Chris, you asked that? It can. Radio will go through something unless it's real big. So they make these radio dishes real big to pick up these long wavelengths that would normally travel through something that's kind of thin. And, this is what I was talking about earlier. The radio waves are the longest waves. Gamma rays are real short. Radio waves are the lowest energy. Gamma rays are the highest energy.
What picks up a gamma ray?
Nothing. We have detectors that can pick them up, but we can't focus them. They have gamma ray detectors that can tell if gamma rays have hit it. Gamma rays will go through almost anything. They're hard to manipulate. But you only get the only thing that's hot enough on Earth to create gamma rays is a nuclear bomb. That's the only thing we can get hot enough to make gamma rays. There's a lot of explosions and stuff in space that get that hot. What were you going to say, Aubrey?
I forgot.
Sorry. So there's a big radio wave telescope.
Whoa.
Now this is a microwave detector. Microwaves are higher energy than radio, but they're still kind of low energy. And these two guys right here use this microwave. That's a microwave telescope. And they use that to help prove that the Big Bang happened. Have you ever heard of the Big Bang?
Boom.
That's the universe. It's said that it started at just an infinitesimally small point and expanded in size until the size we have today. If that really happened, there should be some radiation left over from when the universe was very small and hot to now the universe is very big and pretty cold. There should still be some radiation left from that Big Bang that's long wavelength microwave radiation. They detected it, and it was exactly the wavelength that is predicted by the Big Bang Theory. Not the TV show, the actual Big Bang Theory. And they found it, so they won the Nobel Prize for it. Penzias and Wilson. Have you ever heard of infrared radiation? That's heat. Soldier can put on infrared goggles and see heat going around. If I put on infrared goggles, you would all be glowing brightly. And
Like orange, right?
night vision are a little bit different than infrared. Night vision are they detect light, just like your eyes do, but they can detect very small levels of it. Check this guy out. So, he's got on the bag, and infrared, visible light won't go through the bag, but look, infrared radiation goes right through the bag. This is the picture with an infrared camera, and this is the picture with a normal camera. Do you notice that infrared doesn't go through his glasses?
Yeah.
See, the glasses are dark? Glass absorbs the infrared radiation and won't let it through. This is why your car gets so hot if you leave it out in the sun. Heat can't get through the windows. Light can go right through it, and it heats up the seats, and the heat can't get out. Glass keeps it in. Yeah.
If you leave your windows cracked just a little bit, would it not be?
Yeah, so it wouldn't get nearly as hot. That's what you should
Would
do.
it say to do that?
If you don't not worry about somebody stealing your car.
I mean, if you just left it a little crack.
Just leave a little crack, and it won't get nearly as hot. Yeah. Isn't that a cool picture?
Yeah.
What time's the bell ring? You don't know?
Like, I thought it was
I thought it was now too.
Might be 25 instead of 20.
25. Yeah, it's 25. That's right. Preach. Much preach.
Thanks, bro.
How was it?
It's good.
Huh?
Thanks, bro. Bro.
Now, ultraviolet.
I said bro, but he just said bro. He just said bro.
Bro. No, either one. Ultraviolet is a little bit hotter than something that produces visible light. So if you want to go through the spectrum, here's what you do. You take a hot poker and you stick it in the fire. And at first your hot poker's cold, and it's even a cold object like a piece of iron is giving off radio waves. And probably some microwaves too. But as you heat it up, it starts to get hot. And now the hot poker, you put it in the fire, and if you pull it out, you won't be able to see it glowing, but if you touched it, it'd burn your hands, right? It's giving off a lot of heat. Infrared is heat. But if we get even hotter, then it'll start glowing. That red hot poker will start glowing and start giving off visible light. And it'll go through all the colors of the spectrum. Red, orange, yellow, green, blue, indigo, violet. Y'all know the colors of the spectrum? That is, as it gets hotter, it changes color. And if it's blue hot, that means it's really hot. Or white hot, blue, it's really hot. And then, if you get even hotter than that, it'll start giving off ultraviolet light, which you can't see. But ultraviolet is a type of wave that the sun gives off. This is a picture of the sun with an ultraviolet telescope. That's what the sun looks like. Only the hottest places on the sun are giving off ultraviolet light. Most of the energy the sun gives off is invisible and infrared. It's not in ultraviolet. And ultraviolet is the kind that can give you a sunburn. Yeah. Is that what you're going to say? Yeah. Yeah. So if you lay out, you're not getting burnt from the heat of the sun. You're getting burnt from the ultraviolet.
What are the two things you need? UVA and UVB.
Yeah, there's two. Ultraviolet is separated into categories. Yeah. And then something even hotter will create X-rays. And X-rays can be used to look inside of organisms. This is an X-ray telescope. This is the Spitzer Space Telescope. And it focuses X-rays that come from the stars. Whenever you have a star blow up, it gets hot enough to produce a bunch of X-rays. And we can see that. There is even some X-rays coming off the sun, but not much. And this telescope can focus those X-rays and take pictures using X-rays. And then finally gamma rays. That's a picture of a nuclear bomb. Gamma rays are only given off by the hottest objects. Our sun is not giving off any gamma rays on the outside coming off of it right now. In the middle of the sun, where the hydrogen is being fused into helium, there's a lot of gamma rays. But outside, it's not hot enough. Think of that. The sun is not hot enough to give off gamma